Okay, gang, here's a brief lecture on centroids, center of mass, and weighted position. Okay, so our next section we want to talk about, and I'm going to start by way of a simple example. This is a grade point average calculation. Okay, so let's say, and everybody should, hopefully everybody knows how to calculate their GPA, but here's what we have, right? We've got 3 classes, all biology. Okay, and their corresponding course units. So for example, Biology 101, that's a 5-unit course. Your calculus course you're taking right now may be a 4-unit course, okay? There's the corresponding grades and the grade points attached, right? So B is equal to 3 grade points, C is equal to 2 grade points, and so on, okay? So what's the formula for the grade point average? Well, that's simply put, again, it's just this. We say GPA, and we'll use X with a bar over it. Okay, it's kind of the convention that we use in statistics when we want to talk about an average. And the formula for it is just simply this. Okay, so notice, kids, gang, it's not a straight average, right? It's a weighted average, which makes sense, right? Because not, some courses weigh a little heavier than other courses. Okay, in fact, the way that we calculate our grade, our final grade for our course, right? Quizzes are not as expensive, so to speak, as exams are. So we weight our exams for the final grade as 50% of the final grade, right? Whereas the quizzes are 30%, right? It's a different weight. So same idea here, okay? So here's what we'll get for the following. Note that the X sub I, that represents the grade points, okay? And of course, the sum of all the weights in the denominator. And you can verify, gang, with your calculator, this winds up being 2.93. Okay, it's a weighted average or a weighted position, if you will. Okay, there's nothing special about the formula itself. This formula right here, it just gives you a weighted position. Okay, so for example, if you wanted to consider that, everybody's sitting in a classroom, for example, if you wanted to find the average position of everybody in that class, you would use a formula like this. Okay, there isn't anything special about it. In fact, those of you in physics and engineering, you might consider something like this. Right? Weight is equal to mass times acceleration. And so our weighted position or weighted average would then look like this, right? So I'm going to switch out the weight for mg. And actually, or this, oops, I should have a sub I right here, right? Because it could be that each weight is going to depend on whatever the mass is, okay? Now, the acceleration, of course, is going to be constant, so we can actually factor the g through both the top and the denominator and cancel them directly. And then our weighted position would then simply look like this. Okay, as I said, there just really isn't anything special about the formula. It just gives you a nice, convenient way to determine the weighted position or weighted average of a group of objects or grades or whatever the context of the problem is, okay? I will say this though, again, appealing to your knowledge of physics and engineering, those of you that have had those kinds of classes, let me just make a note here. This particular formula right here, this formula is referred to as giving us the center of mass. Okay, the center of mass. Think of it like as a balancing point, if you will. Okay, let's try an example of something where we want to calculate the center of mass. All right, so let's suppose that we have spread out along the x-axis we'll make this 0, -1, -2, -3, -4, and so on. 1, 2, 3, 4. Okay, and let's say that we have what physics and engineering, they refer to those as point masses. So let's put one right over here at -3. And we'll call that m sub 1 is equal to 12. Maybe there's another one over here. We'll call that m sub 2, and maybe that has a mass of 15 units. And then we'll put another one over here. Let's say that this one has a mass of 20 units. Okay, and what we want to do is we want to calculate the average position or the weighted position of these three masses. And said another way, gang, what we're really saying is, where if we consider this like as a teeter-totter or a lever, right? Where would it balance perfectly? Okay, so that's what we're looking for in a physical sense. Okay, well, I'm just going to use this formula, center of mass, right here. All right, so let's get to it. Okay, and then of course, just add all of this up. We're going to have -36 plus 30 plus 100 over 47. And I didn't leave myself a whole lot of room, did I? I will just move that over. Okay, so let's see, -36 plus 30, what's that? -6 plus 100, so 94 divided by 47. Okay. Okay, now let's extend the logic, right? Let's extend the logic. Let's make another example. And let's say this time we have a series of masses that are spread out in an XY coordinate system. Okay, so we're not along the x-axis now, which we might consider as a one-dimensional case. Now we're going to take our masses and we'll spread them out in an XY coordinate system. Okay, so this might be considered a two-dimensional problem, right? A two-dimensional problem. And let's say we have the following masses arranged in the XY plane as follows. Let's say at 1, 2, 3, at -4, +2, we have a mass equal to 5 units. The next one is at 0.3. And its mass is 4 units. The next one is at 3, 2. And its mass is equal to 3 units. And then finally, there's a fourth mass located at 1, negative 2. And its mass is 6. Okay. Well, we know we've got x bar, right? That'll give us the x coordinate. What we need here is, since this is a two-dimensional case, this is what we need. We need an ordered pair. Okay, we need an ordered pair. We have an x coordinate and a y coordinate because this is a two-dimensional setting. So we know that x bar is given by this formula. What would the one for the y coordinate be? Yeah, good. It would be in a similar way. We will write it like this, right? Okay. Now all we have to do is just calculate both of these values and we'll have an ordered pair. What this will give us, gang, is it'll give us a balancing point. Imagine this. Imagine that those 4 masses are different sized marbles that are set on a tray. And you hold the tray horizontally, kind of like what a waiter and a waitress would do when they're bringing glasses to your table. And what you want to know is what's the exact point where that tray will balance perfectly horizontally. Okay, so we're looking for the center of mass in 2 dimensions. Okay. So for the x coordinate, for the center of mass, okay? And for the y coordinate, in a similar way, all right, let's see what we're going to get. So the second term on here, this is out, is 0. So we're going to get what? Negative 20 plus 9 plus 6. And that's what, 15. So it looks like we're going to get minus 4 over 18. And in the denominator, it looks like we're going to get, let's see, 10, or I'm sorry, for y bar, we're going to get 10 and 12 and 6 and a negative 12. So it looks like that's going to reduce to 16 over 18. And so our center of mass then, our balancing point, is given by this ordered pair. Okay, so for the two-dimensional setting. All right, so the next thing we want to do, actually, I think what I'll do first, before we do the next thing, I'm going to make a remark. This remark, I want to say this. I want to say that a centroid, okay, a centroid. Gang, a centroid is a weighted average, like a center of mass. Okay, a centroid is a weighted average like center of mass, but weighted with a geometric property okay, weighted with a geometric property like area or volume. Okay, like area of, rather than a physical property like weight or mass. Okay, so a centroid, what is a centroid? A centroid is a weighted average like center of mass, but it's weighted with a geometric property like area or volume, as opposed to a physical property like weight or mass. Okay, so this formula, this generic formula right here, which we said there was nothing special about it, right? The weight, whatever the weight is, the W sub I, that just depends on the context of the problem. In the very first example we did, what was the weight? It was the course units, for the previous problems, it was mass, okay? So these two things would become the following. If you're talking about 2 dimensions, switch out the weight W for A sub I. That would be the area of the IF mass, or the IF 2D shape, we'll say. I'll say more about that in a moment. So let me get these formulas down. Okay, so this is the coordinates, gang, for the center of mass for 2-dimensional shapes. Okay, the X sub I, let's make a note. Let's say where X sub I and Y sub I are the coordinates of the center of mass of the ith area. Okay, now the assumption here, gang, is that the areas are all going to have a uniform or a constant density throughout. Okay, we'll say something about variable densities later on, but for now, we talk about our areas, geometric shapes being constant or uniform density throughout. Okay. All right, so here's an example of what that looks like. Let's suppose we have the following, we call it a composite shape. Okay, a composite shape. Okay, with the following, we'll say dimensions. Okay. So what we want to do is we want to find the center of mass, or the centroid rather, excuse me, we want to find the centroid, right? The average position or the weighted position of this composite shape. And so what we do is, again, we superimpose an XY coordinate system on it, like this. Just bear with me here. Okay. All right, I'm gonna draw that in a different. I'm gonna use blue for this now, so I can see it a little bit better on my XY coordinate system. Okay. And I'm going to break it up into 3 separate blue rectangles. Okay, 3 separate blue rectangles. And what I'll do, gang, is I'm going to call this one, the first rectangle, I'm going to call that capital A sub 1. This one I'll call capital A sub 2, and the last one capital A sub 3. And notice the subscript I in the formula here and here. Okay, so that's what I'm talking about. Okay, capital A represents the area of these composite pieces. Okay. Now the next thing, one other thing, I notice, remember we said the X sub I, Y sub I, this right here, those are the coordinates of the center of mass of each one of the areas. Well, by inspection, what's the center of mass of any square, rectangle, circle, or ellipse? Yeah, very good. It would just be dead center, right? Just dead center. Let's use red. And I'll indicate the centers of mass for all 3 areas. Okay, so here's the first one. Here's the second one. And there's the last one right there. Okay, now according to my XY coordinate system, I need the ordered pairs, the coordinates for each one of those 3 dots. Well, okay, we get that. This right here should be this. Okay, all right, so let's label them. Okay, and then we will appeal to our formulas as follows. Let me also, again, point this out as well, since I'm going to need these values anyway. Let me put the following values on our figure, right? What's the area of A sub 3? Yeah, good. It says 4, right? What's the area of A sub 2? Good, it's 3. And what's the area of A sub 1? Good, also 3. Okay, so we're going to need those for our formulas. And here's what we get. All right, that gives us 2.9. So this tells us then, I go up here, that our center of mass for this composite shape is 2.9 and 1. Okay, so 2.9 and 1. So if we were to hold up that blue shape, gang, that one collective shape horizontally, if we wanted to figure out where it was going to balance perfectly, we would hold a pencil point right underneath of the coordinates of this point right here. Okay, so that's the center of mass, or sorry, the centroid of our composite shape. Okay, there's really not much to it. There's no calculus involved at all. We haven't done any calculus. Okay, we're just talking about weighted positions, gang. Like I said, let me go back up here. You know, right back here again. Like I said before, there isn't anything special about this. Okay, it comes up in a lot of different instances, but it is a weighted position, and the weight W just depends on the context of the problem. Okay, yeah. Okay, now, but what are we going to do about irregularly shaped two-dimensional objects, for example, right? What are we going to do about that? You know, this is not an irregularly shaped two-dimensional object, right? It's one shape made up of three rectangles, if you will. Okay, but what about an irregularly shaped uniform density two-dimensional region? What are we going to do about that? Well, let's say this. Let's say, consider the following. Okay, so we'll have a two-dimensional area of uniform region, and let's say that it is trapped between the graphs of two functions, f of x and g of x. Okay, so maybe it looks something like this. And we'll say, as usual, from A to B, yeah? All right, so here's our region. Well, again, the idea is this. It's very clever, and it just depends on, actually, no new math. It just depends on what we talked about above. Here's the idea. Somewhere between the A and the B, let's say maybe here. Okay, I'll locate an X, and then I'm going to draw our differential rectangle the way we've done in the past, right? I'm just going to make it a little bit wider so we can see it better. And the idea is this, right? Theoretically, how many of these rectangles are within this region? And we know that there's an infinite amount of them. So what I'm going to do is I'm going to find the centroid, or center of mass, rather. I'm going to find the center of mass of each one of these red rectangles. For this one, it'll be right here. Okay, now why am I going to do that for all of the rectangles that are in here? Well, consider what we just did in the last example. Go back right here. Okay, when we wanted to calculate the centroid for this composite shape, we broke it up into three blue rectangles. And for each one of those rectangles, we located the corresponding center of mass, right, which was dead center of each rectangle. Okay, well, I'm using exactly the same technique for all of these differential rectangles contained within this region. Okay? And it's going to look like that. Okay, that's going to be my y coordinate right there. All right, so what's the center of mass of that one rectangle? Well, it's x and y. Okay. Now, ordinarily, we would have this, right? Right, for the x coordinate. But there's an infinite amount of these red rectangles, these differential rectangles in there. So you know what's coming next, right? Right? Limits of Riemann sums, we know we're going to need to cross over into doing calculus now, right? So we know that this is going to, in the limit now, is going to lead to the following. Okay, does that make sense? Right, all of these rectangles now, all of these rectangles that are within the region, that's just one of them right there. They're all differential rectangles. What is the area of that one rectangle? Well, gang, it's dA. Okay, that's the area of that rectangle. All right, and so in a similar way, right, in a similar way, this formula for the y coordinate right, as we take the number of rectangles to increase with that bound. And I'm going to make a note where the coordinates x and y, okay, the coordinates x and y. Again, when I refer to the x and y, I'm referring to this right here, here, and here. Okay, so where the coordinates x and y is the center of mass of the differential rectangles okay? Notice the similarities now, okay? Let me go back up here. Okay, we said a centroid is a weighted average, right? Like a center of mass, but weighted with a geometric property. Right now, we're just talking about area, but of course, we could extend the logic to volumes as well, okay? And we said that our formulas would look like this and this. When the weight, it corresponds to area, okay? And what's the capital A? It's the area of the ith region, okay? The area of the ith region, where the x sub I, y sub I, this right here, those are the coordinates of the center of mass of each area, right? Of each different area. And so we just extended the logic yet again, okay? Our areas now are not blue rectangles like in this example, but they're differential rectangles, okay? There's red rectangles that fill up this entire region, okay? All right, let's try an example of that. Let's suppose we want to find the centroid for the region that's bounded by the square root of x equals 4, and the x-axis. Okay. So the first thing I'm going to do is I'm going to introduce somewhere between 0 and 4, maybe here. I'm going to locate my differential rectangle. Oops, that didn't come out very well at all, did it? Let me try that again. I'll make it a little bit wider, okay? Okay. So there's my differential rectangle, okay? And there is its corresponding center of mass. Okay, make sure you label the ends of it like we always do. Okay, now according to this figure, gang, according to this figure, the x coordinate for the differential rectangle is just x. But the y coordinate is the average of the top and the bottom. Okay, in other words, the square root of x plus 0 divided by 2. Got to be careful with that. That's the biggest mistake in these kinds of problems. Okay, the center of mass has x coordinate, or for the differential rectangle now, has x coordinate x, but its y coordinate is going to be the average of the y coordinates of the top and the bottom of the rectangle. Okay, all right, now the area of the rectangle itself, the dA, I'm going to put that over here. It is going to equal the length of the rectangle times the width of the rectangle. Okay. Now our x coordinate oh, that's a mess. Goodness. That's going to look like this. Okay, so in the numerator, our integral is going to range from 0 to 4 of x times the dA, and the dA we calculated above to be the square root of x dx. In the denominator, just the integral from 0 to 4 of dA, which is the square root of x dx. Okay, I'll leave that to you to calculate. Okay, then the y coordinate okay, well, what's the y coordinate of the center of mass? Well, from the figure above, that's going to equal the square root of x plus 0 divided by 2. And then we multiply that by dA, which is square root of x dx. Integral ranges from 0 to 4. The denominator is the same as it was above. Okay, again, I'll leave those calculations to you. All right, again, they're just straightforward integrals. Okay, and when you find them, you're going to have an ordered pair. And that will give you the centroid of this region right here, this blue region. It'll give you the perfect balancing point if we were to hold it up horizontally. Okay. In this example, let's suppose that our region looks like this. So it's bounded above by the square root of x, and it's bounded below by the basic squaring function. Okay, and we want to find the center of mass, or the centroid rather, excuse me, I keep saying the one instead of the other. The centroid, we want to find the centroid of this geometric region, this two-dimensional region, okay? All right, so once again, I'll locate my differential rectangle. Okay, and its center of mass. Okay, now be mindful, gang, the x coordinate for this center of mass is just simply the x. But the y coordinate, right, that's going to be the average of the y coordinates of the top and the bottom of the rectangle. So over here, that's going to look like this. Okay, so keep that in mind now, all right? So let's make some remarks up here. So The differential element of area, our rectangle, has the following area. It's the length of the rectangle times the width of the rectangle. The center of mass of our differential rectangle is x square root of x plus x squared over 2. Okay, we're going to need that for our integrals, all right? All right, let's get the integral. So the x coordinate is going to equal the integral from 0 to 1 of x times dA. Well, dA is above. We just calculated it. So it's going to be square root of x minus x squared dx. Okay, and that's going to be a straightforward integration, gang. You're going to distribute this x through a course, and it's going to be straightforward integration. In the denominator, the integral of dA. Okay, and whatever that is, I'll leave that to you. All right. Then for the y coordinate, our integral is going to range from 0 to 1, and our y coordinate, don't forget, gang, right here. That's our y coordinate for the differential element of area. Okay, and then we're going to multiply that by dA, which is right here. And of course, we need the denominator, which is the same as it was, or same as it is above. And again, these two integrals above and below are just straightforward, and I'll leave those to you, okay? Now, what you'll get, of course, like we said before in the previous example, you're going to get an ordered pair, and that ordered pair will give you the centroid, or the balancing point of this expression right here. Okay, so I will say this. I'm going to leave the calculations to you, but I will say this. Notice the following. I'm going to use a different color. Notice that this region, I mean, my hand isn't very steady, but notice that this region has a line of symmetry. Do you see that? Yeah, it goes right through the middle of it, okay? Do you know what the equation of that blue line is? Yeah, it's the identity function. That's right, gang. It's the identity function. This is the line y equals x. Now, what this tells us is, and it's a principle from physics and engineering, is that if a uniform region, or when I say uniform, what I mean is uniform density, okay, constant density throughout, has a line of symmetry like this, then the center of mass and centroid lie on that line. So what that tells us, here in this example, whatever you get for this coordinate, you better get the same thing for this one. Now, had we pointed that out sooner, right, like before we started all this, then we would say, well, there's no reason to calculate the integrals in y bar, for example, right? All we really need is x bar, and then the corresponding y bar would have to be the same thing because they both lie on the identity function, okay? So we look for those kinds of opportunities when they present themselves, okay? If a two-dimensional region has a line of symmetry like this, and the region is uniform or constant density throughout, then the centroid is going to lie on that line of symmetry, okay? I give those homework problems a try, gang. I think you've definitely got enough here to work on.